All right, so number 11 was one I thought for sure you guys would want to talk about. Some folks stayed after school and kind of talked it out, but I think in the end you should realize, one, the vapor of water or the water gas filled up the initial container that was like 30.6 liters, wherever that is. Yeah, and then as it condensed, it condensed down to its liquid phase, which it said was like 0.99 grams per 0.996 grams per centimeter cubed, which is the same as a milliliter. So you can take the mole of water using the molar mass to the to grams, and then utilize the density to get to a certain volume of that gas, which is the final volume. So 18.07 centimeters cubed is the same as 18.07 milliliters for water anyway. And then we're going to use this as our V final. So since this is in liters on the initial side, the volume has to be in liters as well. So we'll take volume final minus volume initial times the negative P, and that should give us our work to be 30.58 atmosphere liters. Remember, the atmosphere liter is not a unit of energy, so we have to consider converting to joules. So that would be our 101.3. It's 101.325. It gets real specific. Just like the specific heat capacity of water is technically not 4.18. It's 4.14 joules per degree Celsius. So sometimes you'll see that I use the more specific constant. Regardless, though, after you get your work, you had your heat released as 40.66 kilojoules per, or just kilojoules. So you need to convert them to the same unit. You can sum them to be negative 37.6 kilojoules. Good? All right, process questions on the other ones. Random questions, guys. Let's talk. Yeah, JT?
Number 8, I got like negative 1, 1, 1, 1, like 1, 1, but the answer was like negative 11.
Was it the conversion?
And
Did you do positive? Hold on. Let me look at this question. So we had, I don't remember how this question was phrased, but basically you had a volume initial and your volume final. You had to find volume final. So I actually solved for delta V first. So utilizing, it said like all the work that was, all the energy that was released from that compression was 950 joules, but it specifically said all the energy was converted as work as it like recompressed the piston. I think that's what this question was. So as you take your work to be negative 950 and plug it in as W, and your pressure in torr to bring it to atmosphere so we can use that conversion, 0.8553, we are then going to solve for delta V. So the delta V was 1110.7 joules per atmosphere. So as we converted using our atmosphere liter is equivalent to 101.3 joules, we can then cancel joules, cancel atmospheres, and we should get to liters. So that's, it should be about total volume change about 11. So 10.96 liters. And then taking the initial volume they gave you at 0.04 liters, that's how I got overall volume change of 11.
Yeah.
That was a little harder. So if anytime you're trying to solve for like V final or V initial, I would never really solve for those individually first. I would always solve for delta V first, and then go back to solve for that one part of it that you didn't know, because it makes your math a little easier. All right, those were two good questions, okay? So let's finish our notes from yesterday, and then we'll do our lab, okay? So I know the other problem set, there's some that you guys can definitely, you could have done, but I'm going to finish up like 5 and 6 with you specifically today, okay? You have to talk to me, you know this. Someone who was watching our video yesterday said you guys mumble a lot. So yeah, I know. I didn't want to call you out, Megan. Okay. So it'd be great if you could speak out loud, okay? All right, so yesterday we stopped at calorimetry, which was the Q is equal to Q. We talked yesterday about how objects can, of course, absorb energy themselves, which gives us the idea that if we have a, let's say, a styrofoam cup, we have to be able to talk about the energy that styrofoam cup absorbed to account for all the energy that was exchanged in the reaction. So this is kind of where we were at yesterday. And the heat capacity, not specific heat capacity, but heat capacity of an object is not regarding the grams that we have of it in the constant. It's only joules per degree Celsius. So we'll be using this today in the lab. The equation for, let's say, a calorimeter to determine the heat that a calorimeter, like the object that we're testing our stuff in, to determine how much heat it's absorbing itself, is Q cat. Q is equal to cat. So many times we'll call that Q cal because it's the calorimeter itself. We just kind of label them so we know what we're talking about. Is equal to big C delta T. So we will be using this today to determine the heat that a calorimeter absorbs from our reaction. Thumbs up? Okay, so this is what we spoke of yesterday. And just as a reminder, we know specific heat capacity does have grams in it, which is different than the heat capacity we just spoke of, and it's an intensive property. Anybody want to take a guess on what that means? Right, so it's independent of amount, where the extensive property that heat capacity had, just the big C, was an extensive property, meaning it does depend on the amount you have. So like a bigger styrofoam cup would absorb more heat. A smaller styrofoam cup will absorb less heat. But specific heat capacity already has grams, it's already proportional to the grams that are there. So it doesn't matter how much you have. I can have 1 gram of water or 1,000,000 grams of water. The specific heat capacity of water is still what? Yeah, 4.184 joules per gram degree C. So it doesn't matter. It's independent of the mass that you're using. So we many times, since we're in high school, we use those cheap little coffee cup calorimeters, which are styrofoam cups. We won't use like true bomb calorimeters because they're big metal drums, which are pretty expensive. So because of our situation, we will use something that we assume to be at constant pressure. So the pressure in the room is going to stay the same, and there can be some sort of flux of pressure between the cup and the surroundings, so they kind of stay at equilibrium with each other. And a bomb calorimeter, which is like a steel drum, there's a lid on it, and it's metal. If there's a combustion reaction in here, and you're making gases, what's going to happen to the pressure inside of this? It's going to go way up, right? So it wouldn't be constant pressure. That's what we do differentiate between coffee cup calorimetry and bomb calorimetry. So because of this situation, and because of some of the variables that we see, despite the fact that there very well could potentially be a little bit of a delta V, there could be a slight volume change, it's insignificant in our conditions because the flux between our atmosphere and our system. So we generally just call out Q, which is heat, to be equivalent or approximately equivalent to enthalpy. Approximately. But many times we actually will have to go one step farther, which we'll do in our lab, and we'll have to calculate heat by doing Q equals MCAT, and to decide on the enthalpy of a reaction, we then equate that Q, or that heat, back to the moles that it combusted, the moles that were involved in the reaction cell. So we'll take Q and we'll divide it by the moles reacted. So what we're then going to see next is Q is, or delta H, which is enthalpy, is equal to Q over moles. So write that down for now, and then we'll actually utilize that next. So because of some differences in pressure and volume, even if it most times is insignificant, we will generally say that Q is approximately equivalent to enthalpy, but we will need to do the ratio per mole of itself. So these are the states of water and their specific heat capacities. You don't have to memorize them. You just need to recognize when they're different, and we'll be using these in an example shortly. So the one we generally are working with is the liquid water, 4.18, but solid water, which is ice, is going to be a little lower, and then steam is even lower because steam is already moving at such a quick pace, or such a high amount of energy, that it can change temperature faster than liquid water does. And it does deal with their ability to hydrogen bond. So hydrogen bonding comes into play, and as to why these are actually much higher than metals. Thumbs up, can I move on? Okay, we are going to use these constants, so if you didn't write them down, we'll be using them shortly. All right, so quick quiz. Okay, talk to the person next to you. Decide on the first question and the second question. Okay. So you could have multiple answers. You could have multiple answers here. Okay. Take 30 more seconds. All right, come back to me. First question, answer. 4. So it's going to be the one that doesn't have grams in it. So it's just joules per Celsius. That's our heat capacity. That's capital C for heat capacity. Next one. Tell me yay or nay. 1, 2, 3, 4. Potentially. So specific heat capacity is what over what? So energy, right? A form of energy, which is joules most time, over. So I heard mass and temperature. Okay, so this system, energy per mass times temperature is what we're looking for. Is this one of those? Moles can be related to mass, right? So technically, it could be expressed in that way. Okay, what about 5? Certainly, right? 6? No. 7? Yes, because calories could be in place of joules. And 8? British thermal units, BTU, British thermal units. So it's a thermal unit, it's an energy unit. Pounds is a form of mass. There you go. Okay, we'll never use this, but just recognize the system is just energy per gram or mass times temperature. Going on? Okay. Oh, another good question. Take a second. All right, 3, 2, 1, answer. 4. Good, most of us said 4. So, Cassie, tell me why. So the lowest heat capacity or specific heat capacity means that okay, so it requires low energy to cause temperature change, right? It doesn't need as much energy to cause a rapid temperature rise. So which of these will rise in temperature the slowest? Since we know lead, which is going to be the lowest heat capacity, will rise in temperature the fastest. Say again? Aluminum will take in most energy, but it doesn't have as much of an increase in temperature for every joule it gains. Good. Okay, I think that we've already kind of discussed calorimetry enough, but the idea is that we're talking about temperature change or heat exchange between system and surroundings. It can be used in a lot of different processes. Anything that exchanges heat, you can use calorimetry for. What's calor kind of referred to? Say again? Calor kind of sounds like calorie, which is a form of energy, and then what's for you mean? Measurement, right? So energy measurement is what that's referring to. Okay, so we can reference both the exchange of energy being produced and then consumed, or produced and then absorbed. So that's our exo and endo, and it can be used with physical processes and with our chemical processes. But we're going to talk about today with both of those, but we're going to specifically reference chemical. Okay. So this is what the bomb calorimeter looks like. It's pretty fancy. This is what ours looks like. Double stack that styrofoam cup. That baby's a great insulator. Okay, so we will put 2 styrofoam cups together to create a good insulation container. We'll put a thermometer in the top, and then you can have a stir rod in here. You can put a stir rod on the hot plate, but what you do not turn on hot plate? The heat, because one, this thing's, whatever's happening inside is producing the heat. We don't want to give it more heat and then disrupt our chemical or our measurements, right? And what will it do to the styrofoam? Melt it, right? And it stinks real bad. Who's number 1 in our senior class? Binky turned it on last year. I was like, Binky, come on, man. He melted my styrofoam cups. So anyway, you can put a stir rod in there, and you can stir it. Just put the stir function on the hot plate, not the the heat feature. So yeah, we're good there. Oh, but if you want to, which sometimes we do have to relate these things to real life processes where we would use this in real life. Like I said yesterday, I went to Duke Energy Labs. They've got like 15 bomb calorimeters. They're awesome, but they use them for combusting fuel to see how much energy is in their fuel. You can use it for calories in food. Kannapolis Research Center, you guys know where that is? It's in Kannapolis, but it's the big research, like the massive research center. It's nice to go around. Who's ever been to the gym theater there? It's cool. What's their 46? 46 is a restaurant inspired by the number of chromosomes we have because they've done enough research there. They have beakers and flasks on their table. You guys need to go on date night, okay? Anyway, so I think it's Appalachian. They run studies there to measure calories in food and also measure the metabolism of humans. So they put all these like devices, hook them up to you, they measure how much energy you lose, but they put you in a contained room. So you're like in a vacuum, not a vacuum because that would kill you. They put you in a pseudo vacuum and they measure your body temperature and they see how much energy you consume and then how much your body uses. So I almost signed up for one of the research studies, but it was too long term, I couldn't do it. But you make money doing that, college, okay? And then drug pharmaceutical companies, they use them for metabolism all the time to see how much energy your body uses to metabolize drugs, okay? Okay, so give me a thumbs up if you read this question, you understand how to set it up. Read it and give me a thumbs up if you understand how to set it up. Sometimes that's the hardest part. Read it first. All right, so Marcus, tell me how you'd set this up.
First off, you would probably want to set up a table.
So write all of our what down?
All the information for your metals and all the information for your water.
Okay, so all of our givens for both the system and surroundings, and then what?
Then you would need to set up your equation based off of what each one defines. Which
Okay.
in this case is the mass of the metal.
Okay, so what equation do you mean I'm setting up?
MCAT.
So is it just one MCAT?
It's Q equals Q or MCAT equals MCAT.
So Q of metal equals Q of water, right? So which gives us MCAT equals MCAT. And that's MCAT of metal equals MCAT of water. Who is losing energy according to the way this is phrased? Who's releasing energy? The metal is dropping from what to what? 88 degrees Celsius to 32. Like certainly it's going to be releasing energy. So this will be the negative side. Solve for M. Okay, I will do this later. I just want to make sure you can problem solve and get it set up. Okay, moving on. Because this is on your problem set and you guys can practice without on your own. Okay, so as I referenced this now twice, we are going to start to learn how to use delta H, which is called enthalpy. But the simplest way I can make it for you is just remember enthalpy is joules per mole or kilojoules per mole. So enthalpy will just be our Q calculations, which is heat, divided by the moles that we reacted. It will differ in different situations, so I want to do a couple of examples of those before we go to our lab. I just have to work those on. So occasionally, instead of calling it enthalpy of reaction, it can be called molar heat of reaction or just heat of reaction. For some reason, 3 names is like the minimum we have to call things. Okay, so heat of reaction or enthalpy of reaction are 2 other ways to say what we're talking about here. Now, we actually already used this. Do you remember using this yesterday? Joules per mole degree Celsius. It's the same thing as specific heat capacity. It's just not in grams. It's in moles. So hence why it's called molar heat capacity versus specific heat capacity. So occasionally we'll be using that to utilize data to find Q. And then once we find Q, we'll divide it by the moles of things that we reacted, which will give us delta H. So I'm going to specifically work on delta H comb. Doesn't mean like we're combing the reaction and making it react. It means combustion. So delta H combustion is actually what that means. What do you think delta H neut means? Neutralization, and then RXN just reaction is just a really generic way to describe those. So write the combustion reaction for propane. Write the combustion reaction for propane. Please remember prop. Yes. Close to one. All right, what's propane, guys? C3H8. Combustion means what? Plus O2. All combustion of hydrocarbons yield. Okay, and then you start off by balancing what? the C, so we have what here? And then what here? Okay, and then how many oxygens here? So 6 plus 4 is 10. Did I use propane? I wanted to do a specific example. Oh, protein. Sorry, protein. I need to specifically use this one first, okay? So propene C3H6, right? So horrible 6, that's a 6. And then what's here? 3. Okay, now how many oxygens do I have? 9, right? So 9 oxygens. Don't do it yet. Normally, to balance this reaction, we would do what? Basically double all of our coefficients, right? In thermochemistry, you can use fractional coefficients. And that is the only time you can use fractional coefficients, because many times we'll reference like the combustion of 1 mole of propene. So if I doubled all my coefficients, I would have 2 moles of propene, right? And that would be a problem, because if I'm defining delta H as per mole, it needs to be per 1 mole of the propene that I'm combusting. So now I get to use fractional coefficients. So what would I put here? 9 halves. Okay? Don't put 4.5, just put 9 halves. So what I would then write is, according to this reaction, and these states of matter would be described, so this would be gas, 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 and gas, because combustion is probably going to heat this water up enough to be gaseous. We would then write at the end of the reaction, delta H combustion equals blah, blah, blah. Okay, so that would be at the end of the reaction, not like as a product, but just up the side. You guys tell me, do you think this will be endo or exo? It's combustion. Fiery and flaming, right? So it's definitely going to be exo. So it'd be like a negative, 200 kilojoules, a negative 2,000 kilojoules, kind of depends on what we're combusting specifically. Okay, so now we're going to actually solve for a question like this, okay? Ready? I'm reading your mind. You said yes. Great job, guys. Okay. Read, write down your givens first, and then we'll talk. Read and write down your givens first. What variable is that? Say again? Capital C. Just making sure you're kind of labeling as you go. Watch the person next to you and see if you guys can problem solve first. I hear good stuff. I think you're okay. Okay, before you get too far in a rabbit hole, let's get out of the rabbit hole. Some of you guys are like still on the ground. Some of you guys are just burrowing. I don't know where you're going. So I'm looking at all this information. I notice I have a capital C. What is the equation that smacks you with the capital C? Q of the calorimeter equals cap, or big C delta T. Okay, the calorimeter's heat that it's absorbing is equivalent to this. But where's the energy coming from that the calorimeter is absorbing? The what? But what's causing a change in temperature? The combustion of said substance in the bottom calorimeter. So, boom, it combusts in the calorimeter. All the energy that it's given away through the reaction process is being given to the calorimeter. The calorimeter absorbs that energy, but we don't really see the energy absorption. We see the what? The temperature change. We can't measure energy. We can only measure temperature. We don't have any instrument that will measure joules for us. That's why we have to do this every single time. So the calorimeter is increasing by how much? 117 degrees Celsius. Okay? So what's our big C? 2.60 joules per degree Celsius. And then our 117.0 degrees Celsius. So what is the calorimeter's heat absorption? What is it? 304.2 joules. Okay, so if the energy of the calorimeter, if the calorimeter is absorbing that energy, we then have to say, okay, you're positive because you absorb the energy, but where did that energy come from? The combustion reaction, right? So we're going to set this equivalent to negative Q combustion. Because the combustion, this is just us identifying that one is positive, one is negative. You may not always have to write this, but if you do write it, you will always get it right. Because you will have to make sure you include the negative sign. Now, take your Q divided by the moles that combusted. Okay, so negative Q combustion is negative 304.2 joules. We're going to divide that by 28 grams, 52 grams per mole. What's this molar mass? What is the moles? 0.538 what? 5. Okay, so we're dividing by the combustion, or the item combusted, the substance combusted, and this is going to give us negative 556.4 joules per mole. Yes? Yes? Okay. So I know that this, we need to go back and do 6 things, but what we generally will refer to as molar heat of combustion is joules per mole or kilojoules per mole. Because this is a small enough number, I'm not going to convert this to kilojoules because it'd be like 0.5. Yeah.
Can you explain why you're going to negative?
So the calorimeter absorbed energy from the combustion reaction, meaning the combustion reaction is releasing energy. So we must reference that as an exothermic process. So since this specifically is referencing the molar heat of combustion, since we're referencing the exothermic reaction, we must have a negative energy to represent that. And then we divide by our moles that were combusted. Since now these things are talking about the same thing, I can now reference that as the delta H column. Combustion. All right, and then how many sig figs should this have? 3. So then this should be what? Negative what? Joules per mole. and that's delta H. Okay, and if I want to convert this to calories, what do I have to do? So negative 556 or 65 joules per mole multiplied by what? One what? Over, and that would be 135. Can't read my writing. Negative 135 calories per mole. Okay, so now we know how to use molar heat of combustion, or how to solve for molar heat of combustion using molar heat capacities, heat capacities in general, and that we have to take Q divided by moles. Okay? Alright, I might show you like one more thing and we're going to start our lab. Okay, so earlier I referenced all of these. Notice that these are all reactions, right? So if things have to come together, we have to write a balanced chemical equation generally. We have to show reactions happening. For these, similar story, but these are not reactions. It's still Q divided by moles, like if I had a certain number of moles of a substance, but they're all physical changes. So what's that refer to? Vaporization, right? So we have X, that's in its what phase? Liquid phase, going to X in its gaseous phase, and we put delta H that. Tell me, is that an endo process or an exo process? So liquid's kind of chilling, gas is crazy. What did I do from here to here? I added energy, so it's an endothermic process. Good. HF fusion, does anybody remember what that means? Melting, thank you, melting. So X is going to be starting in what phase? Going to X in its liquid phase, and this is going to still be, because we're still going in the same direction on the phase change side of things. And then HF solution, which is what we'll do in our lab, is us taking a substance, let's do sodium chloride in its solid phase. We're going to put it in water, but I'm not going to show it reacting with water, because is this a reaction? Adding sodium chloride to water will just make sodium chloride dissolve, right? It's going to break into what? It's two ions, right? I don't want to show it reacting with water, because that would be hydrolysis of a salt, which would yield an acid and a base. You guys remember hydrolysis? Which is truly a reaction, but in this case, we're not going to show that, because I just want to show the solution process, meaning making a solution. So I put water on top versus H for reactant. So then that's going to make aqueous sodium ion and aqueous chloride ion, which is the solution process is making aqueous ions. So this overall HF solution can be either positive or negative, okay? It's one or the other, but we can't always predict it because we have to know a lot more about the strength of the lattice structure. Remember, ionic compounds are combined in the lattice structure? Do you remember that? Here's what lattice looks like. Okay, so sodium chlorine, sodium chlorine, sodium chlorine, all built up like that. So we have to know a lot more about what's happening with the water and with the solid in order to figure out if this HF solution is positive or negative. That's what your lab is going to figure out, okay? Notice, though, on both of these, and this is specifically for water because we use water a lot, for this example and this example, big difference between HF fusion and HF vaporization. Talk to the person next to you and maybe consider why it's so much bigger. Think about it. All right, Darcy, what you got? I think I heard right.
Well, it's because it's going through different state changes and it takes more energy from liquid to gas than it does from solid to.
So solid to liquid's like, here's a solid, close together, right? There's a liquid, still pretty close together. But what's holding the water together? Which one? Hydrogen bonds, right? So we're overcoming, and I'm not going to say breaking, because breaking kind of references breaking bonds. I say overcoming hydrogen bonding or overcoming IMFs. That's the term that you should be using. Maybe star that, because some people will, like on the exam, they don't give you credit if you say breaking IMFs, because that means that they think you think they're true bonds when they're really not. So overcoming hydrogen bondings, it's just really not a whole lot of separation there, so it's a lower energy requirement. But yeah, going from liquid to gas, you are not only like overcoming, but you are like demolishing the intermolecular forces. You're done, because you went from liquid to gas. right? There's no interaction between this particle and this particle anymore. You knocked them all out. So you have demolished IMAPs here. So it does require a high amount of energy to do that. Okay? All right, we good here? All right, so I'm going to finish. Sorry, I thought I'd get to 5 and 6 on the problem set. I'll do this tomorrow. Okay, hold off on those. Let's look at lab stuff. Okay, so I'm going to do the first part with you. It is called Investigation 12. You have a printout. Did anybody happen to grab an extra one? And no, it says Investigation 12 on it. It was a separate sheet of paper. It was like a total different stack. Looks kind of like this. Does everybody have this? I know now doesn't. This is no. I'll give you my copy. Did you make her an extra by chance? If you did, it's full of this note. And honestly, you all right, so because the first part of this lab is teacher directed, I have to hold your hand. So get ready for some hand holding, people. Okay. So tomorrow, your job is getting ready to you're going to be making hand warmers. Yay! It's not really cold out, but it's eventually going to get cold. So in making a hand warmer, you have to figure out where the heat's coming from to make the hand warmer hot. But there are a couple of challenge requirements to your procedure. So some of this is relevant for your Google Doc procedure. I will share this on my website in a couple minutes, okay? So first, make sure maybe you want to highlight on your own copy. That might be helpful. That would kind of help you get the specific sounds. They may need a highlighter. I will throw highlighters. Anybody? Anybody else? Another? Okay. So a couple of things. I'm not going to highlight on the board here. To make an effective, safe, environmentally benign, and inexpensive hand warmer, your job is that you cannot have your hand warmer increasing more than 20 degrees Celsius, because then you get sued, right? That would be a horrible death there. But you don't want it to get too hot. Your hand warmer needs to be small. No one's going to be carrying around like a gallon of a hand warmer, like, you know, pressing it to their hands and feet. So it needs to be small, 50 milliliters total. Cost as little as possible using the materials I'm allowing you to have, and being as environmentally safe as possible. Okay, so those are some of your requirements. I'll give you a little bit more on the back side of this presentation. So start with the safety and disposal, because you know in your lab notebooks I'm like, not just closed-toed shoes and goggles, guys. Get specific here. We have very specific chemicals that we will be using, so do try to note that you need to be specific in your safety and disposal. Okay, you see that someplace near the materials? Okay, so I have this on a Google Doc for you guys, just because I knew that you would need to look up some of this information, because you will have to, but maybe just put a note to self, safety and disposal, important. Okay, so before we go to the pre-lab questions, we have to watch a quick video with me, okay? There was an animation. The animation link no longer works. I can't depend on anybody these days. So here we go. So it's like 3 minutes. So I'm going to take some notes on the board, and I would write some of those things down too.
Nitrogen atoms of one
It's a great video.
are strongly attracted.
Of 1.87 to pi.
In liquid water, positively charged hydrogen atoms of one water molecule are strongly attracted by the lone electron pairs of negatively charged oxygen atoms from other water molecules. This type of intermolecular interaction is called hydrogen bonding. Every water molecule can form 2 hydrogen bonds through hydrogen atoms, and 2 through electron pairs on the oxygen atom. As a result, intermolecular interactions in liquid water are exceptionally strong, which is reflected by the high boiling point of water, 100 degrees Celsius. In solid ice, water molecules are held together by a regular array of hydrogen bonds. Relatively large empty spaces in the crystal lattice account for the low density of ice, and also explain why ice floats on liquid water.
When an ionic solid is added to water, the polar ends of water molecules are attracted to ions on the surface of the crystal. Positively charged hydrogen atoms bond to anions, while oxygen atoms bond to cations. This attraction distorts the electron clouds around the ions and loosens the ionic bonding within the crystal lattice. At the same time, water molecules at the surface of the crystal are also attracted by other water molecules via hydrogen bonding. As a result, ions leave the crystal lattice and enter the liquid phase. Each of them is surrounded by a number of water molecules arranged in several layers.
The surrounding of ions by water molecules is called hydration. Hydration is an exothermic process, which means that energy...
Okay, 2 things that you should realize so far. What just happened to the solid salt? It got ripped to pieces, right? Okay, think about it. If I have to rip ions from ions, do you think that is going to be an endo process or an exo process? It is karate chop and moves on, right? So what is it? So a karate chop is going to go, release energy, right? It's going to, oh yeah, require energy. Okay, I don't want to karate chop every single day, guys. Okay, so make sure you know that as we took our ionic solid, it was attracted to water, right? So can you guys see my notes? The lights off? Okay. So as you take your ionic solid, it's attracted to water. The O end is attracted to cation, the H end is attracted to anion. This whole process of ripping the ionic bonds apart, ionic bonds broken, is what? Endo or exo? Endo. Put a big endo there. You need to know that. That's step 1, rip ions apart. Step 2, well, water's not automatically just going to remove its own water molecule from the attraction of another water molecule, right? Remember, we know that water and water is attracted via hydrogen bonding. To take water molecule from another water molecule, what am I doing? I'm doing what? I don't want to say breaking. Give me the word. I'm overcoming hydrogen bonds. So do you think that's an endo or exo process? Okay. So I'm taking this water molecule from this water molecule. I'm pulling them apart. Endo or exo? Endo. This is requiring energy. This just doesn't happen by itself. It requires energy to pull compound from or ion water from water. Okay. So let me. I'll include this here. This is 1, 2. Water from water. And to overcome your IMFs is going to be an endothermic process. Okay. So far, ion from ion, endo. Water from water, endo. But then it said. Once the ions in solution, sorry, this is out of order. Once the ions in solution are in solution, the water starts to surround them. They're attracted to each other. And what's the term called for them when water kind of surrounds an ion? Hydration. So that's a super, super strong attraction. Water attracts to the ion in a very strong Coulombic attraction, which is just the opposite charges. This, they said, was what? Very, very exo. Very, very exothermic. So we have a competing system here. We put in energy just to get the ions and water molecules separated, and then we throw them together, and they're like, release energy, they're very stable, it's a very exothermic process. So that's why we have to experiment, because we don't know in the end, is this whole entire process more endo, or is this whole entire process more exo, because the quantity of energy put in and in could still be less than the energy given out. Does that make sense? The magnitudes can differ. Okay.
Is released when water molecules bond to the central ion. In the first layer, the attraction is quite strong, so a lot of energy is released. As the distance from the central ion increases, the attraction of the water molecules weakens and the amount of energy released decreases. At a certain distance away, water molecules are so far away that they are not attracted to the ions at all. This state is referred to as infinite dilution. In this state, no further energy is released from the hydration process. Ions tend to be hydrated by a specific number of water molecules called a hydration number. For example, a sodium cation is hydrated on average by 5 water molecules, while a magnesium cation by as many as 15. The ions of transition metals form coordinate bonds with the molecules in the first hydration layer. For example, when anhydrous copper 2 sulfate is dissolved in water, the first 6 water molecules actually form bonds with the copper ion. The next ones surround the cation in successive hydration layers. During the dissolving of an ionic compound in water, Once an ion is released from the crystal lattice, it is immediately hydrated by a number of water molecules. In this process, some of the hydrogen bonds between molecules of water are broken and replaced by much stronger iron-water interactions. The amount of energy required to break water-water hydrogen bonds is far more than compensated for by the energy released by the interaction of ions with water molecules. So, the hydration process is always exothermic. Enthalpy.
Okay, so we know there are 3 steps to a solution process now, right? First step is what?
First step is to do what, Cassie? Break the ion bonds. You guys see that on my structure here?
Step 1, lattice energy. We'll learn what that means later, but it's just breaking the ionic bonds apart, requires energy. Second step is breaking apart the waters, which is not really represented here, but we're pulling IMFs apart, which requires energy. And then the hydration step is technically the third step, and that's us pulling the ions and water together, which releases energy always. So it's going to be our exo process, which you can see here is exo. But what we're going to figure out is the heat of solution, which is a combination of all those, and we're going to decide based on the quantities of these things if it's positive or negative. Okay? Okay, so I'm going to show you a couple more things here. Whenever you get on your Google Doc, and I'll show you this on my website, you're going to read some information about the background, and there are some pre-lab questions. The pre-lab questions are all related to what we've talked about here. You may not have to do the pre-lab questions in class, though, because I want to make sure we collect our data from the teacher-directed side of things in a couple minutes, okay? So let me show you where that is. Oh, this is, one second. This is, oh, I did say all this about the criteria of design. You guys got that, right? Okay. So, what we're going to do, I'll get back to that in a second. What we're going to do first is we're going to take magnesium sulfate anhydrous, so it's not hydrated. We're going to hydrate it. And when we hydrate it, we're going to measure the temperature change from beginning to end. It's just practicing with our calorimetry equipment and skills. We're then going to calculate the temperature change, and then we can find the Q of that process, the heat of that process. So that's what we're going to do first, and this is kind of how you can set it up. Remember, on the hot plate, you do not do what? Turn on the heat, okay? So in your instructions on your paper and on the Google Doc itself, it tells you specifically what to do. So step 1, magnesium sulfate hydrated. Measure the temperature change. Step 2, we're going to get 2 different temperature waters. One that's starting about 20 degrees Celsius, which is just from the tap. The other, which is about 50 degrees Celsius, which we have to heat up on the hot plate. Okay, then you can turn the hot plate on, the heating element anyway. We're going to put our 2 samples of water together. It's like 100 milliliters and 100 milliliters. We're going to put them together. Theoretically, if I have 20 degrees Celsius and 50 degrees Celsius, and I put them together, what should their average temperature be? 35, right? Now, that's theoretically. What if it only got to 32 degrees Celsius? Say again?
Either one of the temperatures was lower or one of the temperatures.
Let's assume I was perfect in my temperature acquisition. Heat was lost to what? The cup, right? The cup can absorb energy, right? We need to figure out how much energy it absorbs because we're going to use that cup for tomorrow, and we want to know how much energy our cup is absorbing so we can utilize that in our calculations tomorrow, or our percent yield's going to be like 1,000, right, William? Okay, so we want to make sure percent error is low. Okay, so these are your instructions for that, but you'll be writing down your data on your own. Okay, so I'm going to guide you when we get in the back. You guys are going to be in groups because I have to give you specific thermochemistry or items for your lab tomorrow. So these are your groups for tomorrow, meaning you'll start with them today. But these are your samples you're testing tomorrow because there are 6 chemicals you're testing, but not everybody's testing all 6. Okay, so if you guys want to jot down what you're testing tomorrow, that'd be great, and I'll show you this on my website too. Okay, laptops, get to a lab with this group, and then let's chat. Okay, go. Laptops, lab with this group, and let's chat. Goggles, of course. Goggles, of course.
website. I'll show you what this is. Go to my homework website. So I'm going to get a hot plate kind of nearby. Just arrange a hot plate nearby. For today, yeah, rather than being with groups. Can you tell them that the stuff of Okay, so I have a couple requests. This is my magnesium sulfate heptahydrate. I have to dehydrate myself, but I have a 200 gram sample. You need 2 5-gram samples. Okay, so I'm gonna give you, if you give me a beaker, I'm gonna do a scoop of it, and you guys can max out 5 grams. Okay, let's get that done first. For 2 5-gram samples, but regardless, 5 grams. So give me a beaker, I'll scoop out some. You guys need the analytical skills. I also have 2 small scale tests here just for. Who else needs the samples?
Do what?
Alright, so the rest of you, once you're on my website, give me a thumbs up if you found the homework, the link under homework. It should be under tonight's homework. Emily, go grab a little hot for your group. Marcus, we'll have water first and all that. Someone can get the water. Get the water. guys need to create a uniform weight size for your Epsom salt or your magnesium sulfate. I'm giving you more numbers.
You said the secret.
Please read the instructions.
Alright guys, let me repeat our procedure just because some of us are ready to go. Ready? Give me a thumbs up if you got at least 5 grams of magnesium sulfate. That magnesium sulfate should be in your coffee, that magnesium sulfate is going to eventually go in the coffee cup. What's in your, well, it doesn't really matter which way you do it. If you put your magnesium sulfate in there first, what are you putting on top of magnesium sulfate? How much water? 100 milliliters. You're measuring the initial temperature of that water, right? Everybody's a thermometer or you have water probe filled up. Your stir plate should not be on until you are ready to start. Because your stir plate's going to have your magnetic stirring rod in the coffee cup already. Substance is on top. The minute they hit, you need to start measuring temperature change. Okay? Let's go. Let's get that first part done.
For the initial temperature?
You just measure it with import it, and go back and there's
Well, the initial temperature of the water is 20.5 degrees Celsius. Are you ready for this water? I don't think you need the zero, do you? Or you can just go to the symbols and make it reduce them. Huh? Good, man. Yeah. One. Second through response to the test. We got 3,000% there, so that's good. Okay. 20,000. Yeah, you do have a process. Yes. Okay, how do we, I don't want to stick this right down where it's starting. We need to stir it. I'll crush it.
bar on the side was standing up, so your bar is like, that we lights, big bar. It's still, let me see.
Okay, let's see, tell you about second trial then, and then the
My peak is 20.
maybe the hot All right, let's go ahead and run second trials. If you've not done already, start running second trials.
Second trial or one trial? We don't have a little straight, do we? Maybe like at the beach. You can ask them. I got it.
Guys, we will not do the second part of teacher directive, so we will not do the hot cold until tomorrow. Just get your second identical trial done.
Can you dry that out or something? Or I that like street salt? I call it a thing. Yeah, we have some salt on them. But it's part of the food, isn't it? You're wrong, just admit it. There you go. It's so slow. You got it? Alright, face it right off. Jumping jack. Yes.
All right, second trial is almost done. Yeah.
Why would you keep this off between the big waters?
We're just trying to smoke.
No. I watched this, This is very ground up.
Once you get your second data trial, you guys will clean and keep this up there.
Seventh grade.
There's just like a little bit.
Oh.
Oh my god.
You're like, that's why I use the most, that's why I grade yellow stuff first.
Does it feel reflections in? I feel like she really needs reflections. I would if I was the teacher. I don't blame you.
All right, love, you need to finish. We have like 4 minutes left in class, so put your computers up, leave your materials at your desk, okay? Put your computers up, leave your materials at your desk.
Just put it, do that at lab station on it. Put it in his, and then he's going to have lab station on it in there. Hold on, I'm going to wrap up with everybody. Who has CJ? Marcus, thank you. Yeah, I'll have to take attendance. Taz, CJ, and Mary. Thank you. Okay, so we leave in a minute now. You have to clean up now. You have to throw your samples in the drain and save your stir bar. You like literally have to. You have to.
Yeah.
So the link for this, you have it.
Yeah.
Alright, so listen as you clean, okay? Sorry, listen as you clean. That means be quiet. So on the board I have what I expect from you on your Google Doc. So I'm leaving it there. But one, try the pre-lab questions and there's some pre-lab during understanding reading. That reading is essential so that you know what the heck you're talking about. 2, you have 3 substances that were assigned to your group. You are looking at the safety and the cost of those. A lot of this stuff is in the lab itself, but the resources are provided on your Google Doc. 3, design a procedure, just like we did today. Like, do not change anything. Mimic what we did today. This is why we did the teacher directed part first. So, determine a procedure to decide or to calculate H of solution. How do you find H of solution, guys? How do you find SLP? Q over moles, okay? So definitely you're going to have to find a way to find Q and moles. I think you can handle that. For each substance assigned to your group. And remember, those are on my Google Doc as well. And I will do the Q hot and Q cold with you tomorrow to calibrate our coffee cup calorimeter. So I will do that with you. You cannot do that yet just because we didn't have time to do hot and cold today. All right. If you have materials leaving on the desk, I'm not honest, he's not touching labs today, so just it'll be there till tomorrow for you guys, okay? The video. I think that was yesterday. That was yesterday. Okay, I don't think I put anything for tonight. The video, I did it in 2 parts. That's all. So I did the first part of the